What we want to do in this video is find the probability for a sequence of events. So we're going to have these successive trials. And what we want to see is what's the probability of seeing this happen, and then we can add on even more, but seeing a specific sequence of events occur. So wording that we need to be careful of here is that you'll be seeing the word "and" show up in the notation just like we've been using it for those cases of intersections, of looking for the probability of one event and the other, which was the idea of looking at probability of both things occurring at the same time. Thing is, with probability, we use "and" here as well, but we need to be careful of is it represents something very different. And I'll try to bring this up in my wording as much as possible when I go through the solutions here, because while we're writing "and," it's really "and then." We want to see the probability of this and then this. And really, with the notation in our class, if you want to write "and then" instead of "and," you absolutely can. I'm going to write "and" here just so that it matches your other resources in your textbook, but verbally I'll be sure to bring "and then" in, because it's going to bring through a very different calculation. So just be careful here in that with "and," we're going to have two scenarios in terms of probability. What we've seen in the previous videos as the intersection of two events, and then in this video where it's representing a sequence of events of using a connecting word "and then." So when we calculate a sequence of events of seeing the probability of something happening and then another thing, what we're going to use for our calculation is multiplication. So there's going to be two scenarios here, and I even separated the page here. We're going to look at two cases when we have independence versus when events are not independent, or rather dependent. And then this 10% condition is what we'll finish up with, which is just a little piece with independence that'll come up in a few sections that we go through. So with that, let's go to our independent case. So let's say we're taking multiple jelly beans out of the bag. So we're back to our jelly beans, and what we're going to do is draw two jelly beans. And when we do this, we're going to do this with replacement, and this is going to be an important idea here. In fact, I'll scroll down to the picture I drew down for the not independent case, but it's that I have my bag of jelly beans, 1 blue, 2 purple, 3 green, 4 red, and the idea is that when I choose a jelly bean, and I think about taking that first jelly bean, when I go to grab the second jelly bean, I put it back. Meaning when I go to draw the second jelly bean, the bag looks exactly the same. So all my probabilities have stayed exactly the same. So for independence, that's what makes it independent, is that if we have one event occur, it does not change the probability of that next event. So it just stays the same. Then we'll see how that changes when we do remove the jelly beans. But with this, we're working with replacement, so we have our distribution of probabilities, and they're not going to change event to event. So with this, I want to find what's the probability of choosing a green jelly bean, and I'll bring through my multiplication, and then a red jelly bean. So this is where, in terms of notation, I'm writing the probability of green and then red. And this is what I was talking about at the beginning of the video, that this notation looks exactly the same as if I was asking the question, like, what's the probability of choosing a jelly bean that is both green and red, which would be 0 because they don't overlap. So notation-wise, it looks the same, but if you go back to the question itself, it's really asking a sequence where the green jelly bean is event 1, so that's our first event, and then the red jelly bean is event 2. So we have these two events in these successive trials that we're doing. So with that, the rule that we use is that we're going to have multiplication. And in this case, we're drawing 2 jelly beans. I could have made this scenario for drawing 5 jelly beans or 30 jelly beans. We could repeat this process over and over and over again. and that would just make a string of multiplication, and you just want to think about event to event. So first event is getting a green jelly bean. So first event, I want to take that probability of getting a green jelly bean, and then the math I'll do between them is the multiplication, and then I think about what's the next event that I want to see. And the next event is the red jelly bean. So then I multiply with the probability of red. So this calculation here, we'll take that probability of green, which is our first event, 3 out of 10, times the probability of choosing a red jelly bean, so our second event, which is 4 out of 10. And just plug that in a calculator for a 0.12. So with this, how we would interpret it is there is a 12% chance of choosing a green jelly bean and then a red jelly bean. And something I'm going to throw in there is that this is with replacement. Just because that will change the math. In fact, we'll look at a similar scenario down below there that makes the calculation change because it's without replacement, but this case with replacement. So let's see this again. If we're drawing jelly beans with replacement, so we still have our independence there, what's the probability of choosing a red jelly bean and then a purple jelly bean? So probability of first choosing red and then purple. And with this and then probability, we're going to have multiplication between two events in this case. So we're going to take probability of red for our first event and then purple. So the probability of a red jelly bean was 4 out of 10 times the probability of purple, which was 2 out of 10. So this will be a 0.08. So there is an 8% chance. And then, like I was saying in previous videos, then you could just start kind of copying the wording. There's an 8% chance of choosing a red jelly bean and then a purple jelly bean. So I would just copy that down there. So we have independence because the probabilities aren't changing selection to a selection or event to event. The idea being especially focusing on the second event here. So that probability of purple or probability of red, like in this first example, when I go to select the red jelly bean, if I kind of go back to my bag down here, the idea would be that I select a green jelly bean and I took it out and that had a 3 out of 10 chance of occurring. But then I put it back. So that first event had that happen. And then if I go to grab a red jelly bean to choose one of those, 4 out of 10 chance. So it didn't matter that I had chosen a green jelly bean already, it was still 4 out of 10 for that second selection. And if I kept doing this event, if I kept putting the jelly beans back, all those probabilities would stay the same. Blue would be 1 out of 10, purple would be 2 out of 10, green would be 3 out of 10, red 4 out of 10. It would stay the same every single time. So when you have independence and you're looking for the probability of one event and then, and even though it says and there, it's really and then, you would multiply the two probabilities. So let's see what happens when we work without replacement. So what's the probability of choosing a green jelly bean and then a red jelly bean? So this is a lot like the first example we looked at up above. In fact, I'll even write it the same as probability of green for event 1 and then red. Now, we're still going to have multiplication here. So with green and then red, we're still going to think multiplication between two events here. The first event is still, I'm getting my first jelly bean, what's the probability that it's green? So what I would do is think about selecting one of these, and there would be a 3 out of 10 chance. So nothing really changes there. That's still just the probability of green. When I go to my second one though, if this is without replacement, it's that I chose that green jelly bean and now it's gone. I ate it, it doesn't exist anymore. When I do that, the structure of the bag changes. I have 1 blue, 2 purple, 2 green, 4 red. So the number of green jelly beans changed. Also, my sample size changed, where I started with 10 jelly beans, now I only have 9. So when I go to find the second probability, what I'm really thinking of here is the probability of choosing a red jelly bean given I already selected 1 green jelly bean. So this probability of red, now that the bag has changed, well, I have 4 red jelly beans out of the 9 remaining there. So we can't just multiply by 4 out of 10 because we don't have 10 jelly beans anymore. If we're working without replacement, the probabilities change, which makes this not independent. So with this, we multiply those values, which will be a 0.1333. And then my wording will look really similar as up above. Mostly I'll just throw in that it's without replacement. So I'll say there is a 13.33% chance of choosing a green and then red jelly bean without replacement. All right. So let's look at one more here. We're going to draw jelly beans without replacement, so it's not independent. And we're going to look at the probability of choosing a purple jelly bean and then a green jelly bean. So again, I'm going to think of probability of purple, and then we're going to multiply with the probability of green given we've taken out 1 purple. This notation I'm writing is very rough for the second piece. The second piece that we're putting here is actually a conditional probability, which is going to be in our next video. So I'll have more accurate notation then when we talk about it, but we can still have this idea of what the conditional probability is. So first event, probability of purple, 2 out of 10 chance. So when we do that, we would find our purple jelly bean, just choose one of them, and it's no longer in the bag. It's gone. So now we only have 1 purple out of 9 total jelly beans. So probability of green, given that we've already selected 1 purple jelly bean, well, we have 3 green jelly beans out of our 9 total jelly beans. So with that, this would be a 0.0667. So there is a 6.67% chance of choosing a purple jelly bean and then a green jelly bean without replacement. So our multiplication rule for dependent events, when the probabilities change, it's going to be multiplication. It's just the probability of the next event. We need to think step by step of how our sample space is changing as we remove things when we're working without replacement. Whereas when we're working with replacement, it isn't changing. So we don't need to worry step by step really. We can start with our main probabilities and then just use those values. But when we don't replace, we need to think about kind of like how I drew a picture over here of how that changes step by step. So this piece right here, the second piece with the probability of B given that A has already occurred, this is a conditional probability, which we'll talk about more in the next video. But even without the notation of the next video, it's exactly what we're doing here, that there's this condition that has already been met. So how did the probability change? One last little piece that I want to end with here is the 10% condition. This helps with using independence, because really our rule with independence is nice because you just use the probabilities. You don't have to think step by step. Like I was saying, you would just have your initial probabilities and then just use those values for multiplication. Now, things like selecting people and selecting things typically working without replacement, you rarely want to have the same values come up, especially like if I was selecting a group of 5 students. I would want to do that without replacement because I wouldn't want someone to be in a group twice. It wouldn't work with people. So there is a factor though, where if we are working without replacement, which without replacement is typically dependent, so we'd have to think about step by step, there are factors that can come up where even though it's without replacement, even though it's technically dependent, if the situation is correct, we can actually work with it in an independent manner, which is nice. It's more convenient for us and lets us work with easier numbers. So we'll look at an example with this. But the idea is if we sample less than 10% of the population, we can assume we have independence. So then we could just use that rule where we can multiply the probabilities without having to think about conditions and how it's changing step by step. So this rule doesn't work for the jelly bean scenario that we just looked at. We had 10 jelly beans and we were sampling 2 of them. That was too large of a portion. That's over 10% of our population of 10 jelly beans. So it wouldn't work up above. Where it would work is in this scenario, if we're looking at all Americans, so that would be our population, and what we're going to do is select 2 Americans. Doing that, selecting 2 out of all Americans, just choosing 2 of them is definitely less than 10% of all Americans. So with this, we're sampling a small group from a much larger entity. What they tell us is blue eyes for Americans has a 17% chance of occurring. So I'm going to write that down. We have this probability of blue eyes is 17%. And we're going to go ahead and estimate that the population is about 329.5 million people. So if I'm selecting 2 people and say I want to look at the probability of selecting someone with blue eyes and then another person with blue eyes. So selecting people, this would technically be without replacement. So I would have to use my rule that's up above here of, okay, what's the probability of someone with blue eyes? And then times, what's the probability of selecting someone with blue eyes given that we've already taken someone out of the population that has blue eyes? So numerically here, I'm going to show you numerically what happens. It's kind of messy because these numbers are absolutely huge, but it kind of proves the point. So 17% of the 329.5 million Americans have blue eyes. That calculation there would just leave you with 56,015,000 Americans with blue eyes out of the 329.5 million Americans. So that right there is our 17%. That's what it would equate to. So we would have this for our first event, probability of choosing a person with blue eyes. Then for our second event, if this is sampling without replacement, then we would need to think about our conditional probability. What's the probability of choosing someone with blue eyes given we've already selected someone with blue eyes? Well, what we would do is bump down the numerator by 1 because we took one of them out of the population. So we'd have, this is where it's going to get nice and messy. Here we go. Out of, and then we already selected 1 American, so that denominator would also bump down by 1. And this would technically be the correct way to go about it. But even though it's the correct way to go about it, what you'll notice if you plugged in this second number into your calculator, as messy as it is, you'll get like 0.169999999. Essentially, it would round to 0.17, which basically means we just use the rule for independent events. It really is just this probability of blue eyes times probability of blue eyes. Because having such a large population And looking at such a small portion of that population, that fraction's going to stay at 17% each time we select blue eyes. So with that, we don't really need to think as we did with the jelly beans and how these fractions dramatically change because we have such a small population and we're taking a larger portion of it. When we work with a large population and sample such a small portion, instead of worrying about these big messy fractions, what we could have done is just skip all of that. And because we're sampling 2 out of all Americans, we can assume we have independence and just use our rule with independence of taking the probability of blue eyes times probability of blue eyes. So this 10% condition is going to come up every now and then in that we can assume we have independence when we sample a small portion of our larger population.